Hey everyone, in this video we're going to go over section 5.1, area and distance. Up until this point we've been doing what they call differential calculus. We've been taking derivatives, we've been discussing rates of change, and we've been gaining information about functions from those derivatives. Chapter 5 is the beginning of what they call integral calculus, for reasons we'll discover later. So now we have a new problem in mind. Our new problem is this. What is the area S of the region that lies beneath the curve y is equal to f of x between x is equal to a and x is equal to b? So example 1. We want to use rectangles to estimate the area under the curve y is equal to x squared between 0 and 2. So let's get a graph. Between 0 and 2. I'm sorry, I meant to write between 0 and 1. Okay. So, here's 1, here's 1/2, here's 3/4, here's 1/4, and this is a height of 1. So, we want to use rectangles to estimate the area under the curve. We could use one rectangle. If we use one rectangle, then we've got this height of 1, and we would have this width of 1. But we can tell that the area underneath this curve, and this is that region S, we can tell that this area is a lot less than 1. In fact, we can tell that a triangle is even an overestimation. But we're not supposed to estimate it with triangles, we're supposed to estimate it with rectangles. How accurate your estimation is depends on the number of rectangles you use. And we're going to have a discussion about several different numbers of rectangles you can choose. For the sake of demonstration, we're going to choose 4 rectangles. Or n is going to equal 4, and you'll see where that n comes into place here in a second. So, we're going to use 4 rectangles. So, we've got this number line, coincidentally, evenly divided into 4 equal sections. If you look, that means the width of each of these rectangles is going to be 1/4. From 0 to 1/4 has a width of 1/4. From 1/4 to 1/2 has a width of 1/4. From 1/2 to 3/4 has a width of 1/4, and from 3/4 to 1 has a width of 1/4. So regardless of the height of any of these rectangles, all of their width is going to be the same 1/4. So now we need to have a discussion about how we get the heights of these rectangles. Well, we're going to get the height of these rectangles from this curve, y is equal to x squared. Or, for the sake of argument, let's call this thing f of x. F of x is equal to x squared. So we're going to use the formula we were given to come up with heights for our rectangles. We're actually going to do this example in 3 different ways. The first 2 go with each other. And I'm going to draw 2 curves, and they're supposed to be the exact same. They're the same curve, y is equal to x squared. So here's 1, 1/2, 1/4, 3/4, 1, 1/2, 1/4, 3/4. Okay, so we can either get our heights, and this will be left, right. So, notice how this region, we've got the interval 0 to 1/4. Then we have the interval 1/4 to 1/2. Then we have the interval 1/2 to 3/4. Then we have the interval 3/4 to 1. I wrote a little too cramped. But this interval goes here, this interval is here, and this interval is here, and this interval is here. When we use our left end points, we get our height from the left endpoint. This is the x value for our height. This is the x value for our height. This is the x value for our height. And this is the x value for our height. Let me show you what I mean on the next page. So that means our height is going to be given by, or I'm going to call this region S. S is going to be approximately equal to our height when x is equal to 0 times the width of this section plus the height evaluated at the left endpoint, f of 1/4, times the width of this section, 1/4, plus the height evaluated when x is equal to 1/2, times the width of this section. And then finally, we'll add the height when x is equal to 3/4 times the width of this section. So what we're doing is we're getting the height here, then we're getting the height here, and then we're getting the height here, and then we're getting the height here. Looking at the picture, we're just going to add, well, we're really adding 4, but f of 0 is 0 squared times 1/4 plus 1/4 squared times 1/4 plus 1/2 squared times 1/4 plus 3/4 squared times 1/4. So it's really 4 squares, it's just one of them has a height of 0. So let's figure out what we think S is. So that would be equal to 0 plus 1/16 times 1/4 plus 1/4 times 1/4 plus 9/4 times 1/4. Well, if I factor, 9/16 times 1/4. If I factor out a 1/4, this is equal to 1/4 of, we would get 1/16 plus 1/4 plus 9/16. I just factored out this 1/4, this 1/4, and this 1/4. 1/4 is the same as 4/16 plus 9/16 is 13/16. Plus 1 gives us 14/16. So this is 1/4 of 14/16. 2 and 7, this is equal to 7/32. Which, for the sake of argument, is approximately equal to 0.21875. Perfect. So this is our estimation using left endpoints. Since we estimated this with 4 rectangles, we call this number L sub 4 is equal to 0.21875. Now we'll repeat the same process with our right endpoints. I'll put that over there. And so we still have these same intervals. We're still going to break this up into 4 sections. We've got one right here. We've got a width of 1/4. We've got another width of 1/4. We've got another width of 1/4. And we've got another width of 1/4. So we've got these 4 sections. This first section is the interval from 0 to 1/4. Then we have the interval from 1/4 to 1/2. Then we have the interval 1/2 to 3/4. Then we have the interval from 3/4 to 1. Since we're going to do our right endpoints, that means we're going to get our heights of our rectangles from these right endpoints. In the picture, this is what we're doing. And you can see now we're going to overestimate. The area. But let's figure it out. Let's figure out what this is going to be. So that area S is going to be approximately equal to, well, we get our height when x is equal to 1/4, f of 1/4 times the width of this rectangle, which is 1/4. Then we'll add our height when x is equal to 1/2 times the width of this rectangle, which is 1/4. Then we'll add the height. Times the width for this rectangle, f of 3/4 times 1/4. Then finally, we'd get f of 1 times 1/4. This is equal to 1/4 squared times 1/4 plus 1/2 squared times 1/4 plus 3/4 squared times 1/4 plus 1 squared times 1/4. And if we factor out the 1/4, this will give us a 1/4 of 1 over 4 squared is 1/16 plus 1 over 2 squared is 1/4 plus 3/4 squared is 9/16 and 1 squared is 1, which for the sake of argument is 16/16. Oh, this is equal to a fourth of 1/16 plus 4/16 plus 9/16 plus 16/16, which is 1/4 of 30. 20 plus 10 is 30 over 16, which is 15 over 32, which, for the sake of argument, is 0.46875. And just like before, how when we used our left endpoints and we called it L4, we used our right endpoints with 4 squares, so that means we would call this R sub 4. That's equal to 0.46875. So I only have right endpoints programmed up. So you saw that when n was equal to 4, we had our right endpoints working out to be 0.46875. Here's a picture I didn't draw of that. So the sum of the area of these 4 rectangles was 0.46875. Now, if we increase the number of rectangles, we go from n is equal to 4 to n is equal to 10, we get this picture. We have all of these rectangles. And if you look, it looks like there's less area above the curve. In fact, we can overlay these two, and you can see that, yeah, this big rectangle appears to have a bunch more stuff added extra. And in fact, as the value of n increases, how much we overestimate or how much we underestimate goes to 0. Let me say that differently. As n goes up, the error in our estimation goes down. So now we're going to return back over to paper, and I've got a chart for you. So as we let the value of n get large, look at what happens to the value of L sub n and R sub n. When n is equal to 10, this is where we're at. N is equal to 20, 30, 50, 100, 1,000. And if we were to let n tend to infinity, we're going to assume that the true value of s is somewhere in between these two values. 3338335 and 0.3328335. But we can do even better than this, and this is our idea as we let n go to infinity. And in fact, for example 2, we're going to do just that. In example 2, we're going to show that s is equal to, well, this looks like it's about 1/3. That is, we're going to show that the limit as n goes off to infinity of r sub n is equal to 1/3. Perfect. Let's get set up on a new page. Okay, so we'll show that the limit as n goes off to infinity of r sub n is equal to 1/3. And remember that this curve is y is equal to x squared. And this is still over the interval from 0 to 1. So first, let's come up with a nice formula for r sub n before we worry about these limits. For our first example, we knew that I was going to say, r sub 4 was equal to, let's see, that was, r sub 4 was equal to the height times the width, plus the height, and I'm going to write it as 2/4 times the width, plus the height times the width, plus the height, and I'm going to write it as 4/4 times the width. Well, that gave us 1/4 squared times 1/4 plus 2/4 squared times 1/4 plus 3/4 squared times 1/4 plus 4/4 squared times 1/4. And we've done all this algebra already. Well, let's figure out what we think. What about R8? Just to get us an idea. Well, now we would have this square and 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 then this square and this square. So now we have these 8, and now we have this width of 1/8. And getting our right endpoint, this would give us our height evaluated at 1/8 times our width of 1/8. We go that width over again, see that we'd add f of 2/8 times our width of 1/8. Then f of 3/8 times 1/8, and this pattern would continue until we get f of 8/8 divided by 1, or times 1/8, which would give us 1/8 squared times 1/8 plus 2/8 squared times 1/8 plus 3/8 squared times 1/8 plus 8/8 squared times 1/8. And before we divide this up again and do this in 16th, let's look at the similarities. Let's see if we can figure out what r sub n would be from this. Well, when we had r sub 4, we had 1/4 squared, 2/4 squared, 3/4 squared, and a 4/4 squared. When r was 8, we had this 1/8 squared, 2/8 squared, 3/8 squared, and 8/8 squared. So r sub n is going to have a 1/n squared times something plus a 2/n squared times something plus an n/n squared times something. And what that something is was, well, our width. When r was 4, our width was 1/4. When r was 8, our width was 1/8. And in fact, our width is actually going to be given by the difference of our endpoints divided by n, which is just going to be 1/n. Well, let's simplify this a little bit. This is going to be, I've got an n times an n. All of these terms have an n cubed in the denominator. So I'm going to pull out a 1 over n cubed. And what's left is we're going to have a 1 squared plus a 2 squared plus an n squared. Now this isn't something this is something I recognize, but I've yet to etch it into my mind. The sum of the first n digits squared is n times n plus 1 times 2n plus 1 all over 6. So let's running out of space, I'm going to rewrite this right here. We have r sub n being equal to 1 over n cubed times n plus 1 times 2n plus 1 all divided by 6. We can simplify this. One of these n's will cancel out with that n, and we get r sub n to be equal to n plus 1 times 2n plus 1 all over 6n squared. So what we wanted to do was show the limit as n goes to infinity of Rn was equal to 1/3. So we want to take the limit as n goes off to infinity of r sub n plus 1 times 2n plus 1 all over 6n squared, which is the limit as n goes off to infinity of n squared plus 3n plus 1 all over, 2n squared plus 3n plus 1, all divided by 6n squared, which is equal to the limit, as n goes off to infinity, of 2n squared divided by n squared is 1/3, plus 3n divided by 6n squared gives us 1 over 2n, plus 1 over 6n squared, and as n goes to infinity, that equals 1/3. So, for good measure, and we don't do it in this class, I don't think I did it when I was in a calculus class, you would want to show that the limit as n goes off to infinity of r sub n is equal to the limit as n goes off to infinity of L sub n. Makes sense with what we know about derivatives. It makes sense that we need limits as we go from one direction to equal limits as we go to the other. But we don't have to do that in this class. This takeaway, though, was how I was able to symbolically manipulate this equation. How I started off with something easy. I only did R4 and R8 as a demonstration to show us a pattern emerging, or help you guys try and find the pattern that's supposed to be emerging. But when you're trying to come up with these, you write what r sub n is purely symbolically, and you manipulate it. Usually you're going to have to use something like a sum of squares formula, a sum of first integers formula. This is something that I wouldn't put on the test in this way, because I wouldn't want the problem to hinge on you guys remembering that the sum of the first digits, the first n digits squared is equal to this. But you will probably on your homework have to symbolically manipulate something to show that a limit is equal to a value. Well, before example 3, let's generalize this idea. Let's talk about what we have up to this point. Cool. And this is our curve y is equal to some function of x. And so what we're talking about doing is we're talking about dividing this thing up into a bunch of different regions. And these aren't rectangles or anything like that. These are just our regions. Our slices, if you will. And so for now, I'm going to call this value x1, x2, x3. If we skip over some, I can call this value x sub I minus 1. And I can call this one x sub I. This would be x sub I plus 1. We call this one x of n minus 1. And we call this endpoint b. You could also call b x sub n. So, what our idea is that we want to get our heights. We want to somehow approximate this area. And we've done this in a couple different ways. We've used our left end point to get this rectangle. We've used our right end point to get this rectangle. We could also use our midpoint. Our midpoint, we would pick the value right in between, and get this height, and we would approximate this region with this rectangle. We didn't discuss midpoint in the previous example, but for all of these, we have our regions. Our regions are a to x1, x1 to x2, x2 to x3, and then we'll have xn minus 1 to xn. So, for our left midpoints, we use the values on the left. Our left is going to be equal to f of a times our width. Well, all of these width, delta x, is going to be equal to, and by width we just mean our change in x, is going to be our endpoint, or the difference in our endpoints divided by n. And so this delta x is this step going from a to x1. And from x1 to x2 is our delta x. And from x2 to x3 has a width of delta x. So we would get f of a times delta x plus f of x1 times delta x plus f of xn minus 1 times delta x. Well, if I was able to call b xn, would you guys believe me if I called a x0? So we could call this f of x0 delta x plus f of x1 delta x plus f of xn minus 1 times delta x. So this is our idea for our left endpoints. For our right endpoints, and we'll talk about delta x here in a second. For our right endpoints, we use these values. F of x1 times delta x, because we have a height times a width, plus f of x2, height times a width, plus f of xn times delta x, because we're using our right endpoints. Now, for our midpoints, I guess I'm doing this one in blue, we want the midpoint of these. So the midpoint is going to be x1 plus a divided by 2 times delta x. To that we're going to add f of, now the midpoint of this interval is x2 plus x1 divided by 2 times our width, plus the last one would be f of x sub n plus x sub n minus 1, all divided by 2, times our width. So, left endpoints, we're breaking these up into, well, let me back up. We break this interval up into n chunks. Each one of these chunks is going to have a width of delta x. Not just delta, delta x. Delta x is going to be the difference in the endpoints divided by 2. Okay, so now we're either going to approximate the area of this region with a left endpoint, a right endpoint, or a midpoint. Well, this region is bound by a and x1, so our left endpoints, we're taking these left endpoints. For our right endpoints, we're taking these right endpoints. The midpoints are kind of tricky. You have to ask yourself, well, what's the midpoint of this interval? How do I figure it out? Well, you add them and divide by 2. How do I figure out the midpoint of that interval? You add them and divide by 2. So this is the overall idea, where we're taking the width of this unit, and it's just how do you come up with the height? Which one do you choose? Realistically, you wouldn't use rectangles in the real world. You would use different shapes. Trapezoids are a lot better. But this is supposed to get you guys used to the idea. Also, so if we start at A, let's put this over here. If we start at A, our next jump is x1. But if you look, x1 is just equal to a plus delta x. x2, well, we started at x1, and we added delta x to it. But we know what x1 is. That's a plus delta x plus delta x. And we get x2 is equal to a plus 2 delta x. x3 is going to be x2 plus delta x, which is equal to a plus 2 delta x plus delta x. And we get x3 being equal to a plus 3 delta x. That means x sub n is going to be equal to a plus n delta x. So we can simplify these formulas a little bit more. Before I just throw all the symbolism at you at once, I want to work out an example with you. Let me get set up. Well, before we move on to example 3, let's talk about this definition. This just formalizes the drawing that I just had up. It says the area of a region S that lies underneath the graph of a continuous function f is the limit of the sum of the areas of approximating rectangles. That is, the area is equal to this limit. What we're doing is we're using these approximating rectangles where we have a height and a width, and we're adding up the area from that rectangle, and we're adding up all of these areas as n goes out to infinity. I believe you guys have seen the sigma before. To denote recursive summation, kind of like you could write 1 plus 2 plus 3 plus 4 as the sum as I is equal to 1 to 4 of I. You could, the sum as I is equal to 2 to 5 of the sine of Ix is equal to the sine of x plus the sine of 2x plus the sine of 3x plus the sine of 4x plus the sine of 5x. So this sigma just denotes recursive addition. This means that as a refresher, this means that as a refresher. So now let's start with example 3. Alright, so let A be the area of the region that lies under the curve y is equal to e to the negative x between x is equal to 0 and x is equal to 2. The first thing we're going to do is we're going to use right endpoints to find an expression for a as a limit, and we're not going to evaluate that limit. And b, we're going to estimate the area by taking sample points, by taking the midpoints of our intervals to be the sample points, and using 4 sub-intervals and 10 sub-intervals to estimate a. So, part A. Using right endpoints. What that's getting at is using that definition that I have, where a was equal to the limit as n goes off to infinity of the sum of I is equal to 1 to n of f of x sub I times delta x. And what we're looking to do is we're looking to come up, we're trying to match this with this information. So dealing with our xi's. Well, we'll start off with our delta x. Delta x is equal to the difference in our endpoints, 2 minus 0, divided by n, which is just 2 over n. That means x sub 1 is going to be equal to 2 to the n. I'm sorry, x sub 1 is going to be equal to 0. That means x sub 1 is going to be equal to 2 over n, and x sub 2 is equal to 2 over the n plus delta x, which is 2 over n, which is 4 over n. X sub 3 is going to be 6 over n, and we're going to keep on with that pattern. Perfect. So let's just write this again. A is equal to the limit as n goes off to infinity of the sum from I is equal to 1 to n of f of xi times delta x, where f of x is equal to e to the negative x, and we have delta x being equal to 2 to the n. So filling this information out where it goes, we get a is equal to the limit as n goes off to infinity of the sum of I is equal to 1 to n. So we can call this, how about we just call it e to the negative x sub I times delta x, which is 2 over n. Well, on the back side, we saw that x1 was 2 to the n, and x2 was 4 to the n, x3 is 6 to the n. We can think of this as 2 times 1, and that as 2 times 2, and this as 2 times 3. So a pattern is emerging, and our exponents are of the form e to the negative 2I over n. We'd have 2 to the 1 divided by n, 2 to the 2 divided by n, 2 to the 3 divided by n. That negative sign is that negative sign, which is that negative sign. It's just been there all along. Times 2 to the n. So this is the limit. This is using right endpoints to find an expression for a as a limit. Done. We don't have to evaluate this thing, which is perfect. Now moving on to part B. We're going to estimate the area using midpoints and sub-intervals, and we're going to do it with 4 and with 10 intervals. So, if y is equal to e to the negative x, and we're going from 0 to 2, we had delta x. Delta x is going to equal to 2 minus 0 all over, and for this example, n is equal to 4, which is equal to 2 over 4, which is equal to 1/2. So that means our 4 intervals, because we're breaking this into 4 intervals, are 0 to 1/2, 1/2 to 1, 1 to 3/2, and 3/2 to 1. Well, we're doing our midpoints, So we need the midpoint of this interval. Halfway between 0 and 1/2 is 1/4. Halfway between 1/2 and 1 is 3/4. Halfway between 1 and 3/2 is 5/4. Halfway between 3/2 and 1 is 7/4. These are the x values that we're going to use to get the heights of our rectangles. We get m sub 4. The sum of the first four midpoints is going to be the height evaluated when x is equal to 1/4 times the width of our interval, which is 1/2, plus the height when x is equal to 3/4 times the width of our interval, plus the height of the rectangle when x is 5/4 times the width of our rectangle, plus the height of the rectangle when x is 7/4 times the width of our rectangle. This will give us 1/2 times e to the negative 1/4 plus e to the negative 3/4 plus e to the negative 5/4 plus e to the negative 7/4. At this point, you plug it into a calculator. I've got to turn the page, and we get m sub 4 to be about 0.8557. I am going to skip this part and a majority of that part, but when n is equal to 10, the setup is delta x is equal to 2 minus 0 divided by 10, which is equal to 1/5. Our intervals are going to be 0 to 1/5, 1/5 to, and I'm going to leave it as 2/5, 2/5 to 3/5, 3/5 to 4/5, and then 4/5 to 5/5. It continues because we're going all the way out to 2, but I'm not going to write out 10 of these. Now for our midpoint, we do halfway between 0 and 1/5 is 1/10. Halfway between 1/5 and 2/5 is 3/10. 5/10. 7/10. 9/10. And there's going to be 5 more. We would get 11/10, 13/10, 15/10, 17/10, and 19/10. And all of these are giving you your x values that you get the heights for. So the formula for the solution would be f of 1/10 times a width of 1/5 plus f of 3/10 times a width of 1/5 plus f of, that would be 19/10 times the width of 1/5. You would go through and crunch the numbers for all that, and you would get m sub 10 to be about 0.8632. So, an example of the distance problem is this. Suppose we're driving a car with a broken odometer. An odometer is that number usually in the middle of your speedometer that tells you how many miles are on your vehicle. So the gauge that tells you how far your vehicle is has driven is broken. But you want to get an idea of how far you've been driving, or how far you've driven over a certain length of time. And so you recorded your speed in feet per second at different times. Every 5 seconds you recorded your speed, and you want to figure out how far you traveled in that length of time. So there's a couple different ways you can think about it. Either way, all of these widths have, all of these intervals, I would say, have a width of 5. And instead of calling it delta x like we have been, I'm going to call it delta S for seconds, our change in seconds. Delta S is always going to be equal to 5 in this problem. And so what you can do, we're just trying to approximate right now. It should make sense that knowing the rate, our rate of change in position should be able to give us some information about our position. What we're going to do is we're going to estimate that our speed was constant over these units of time. And there's two ways you can think about it. You can either, on one way, think for over 0 to 5 seconds, you are 25 mph. And from 5 to 10, you were from 0 to 5 you were 25. From 5 to 10, you're 31. From 10 to 15, you're 35. From 15 to 20, you're 43. From 20 to 25, you're 47. And from 25 to 30, you're 45. And let's put some brackets and a couple commas. So, if we've got a rate times time, well, a rate times a time is equal to a distance. So, on one hand, we could have our rate is 25, not miles per hour, I'm sorry, feet per second. 25 feet per second times 5 seconds, plus 31 feet per second times 5 seconds, plus 35 feet per second times 5 seconds, plus 43 feet per second times 5 seconds, plus 47 feet per second times 5 seconds, plus 45 feet per second times 5 seconds. If you calculate that, that would equal 130 feet. Well, instead of saying we drove that fast over that time interval, how about we say we drove that fast over that time interval? The other equally valid estimation would be that we drove 31 miles per hour for the first 5 seconds, and then we drove feet per second for the next 5 seconds, and then we drove 43 feet per second for the next 5 seconds, and then we drove 47 feet per second for the next 5 seconds, and then we drove 45 feet per second for the next 5 seconds, and then finally 41 feet per second for the final 5 seconds. If you were to crunch that number, we would get 1,210 feet. So, once again, we're probably getting some sort of underestimation and some sort of overestimation. But it's the idea. The same idea is we have some width, and we're just approximating area under curves with rectangles. We have a width, we have a height, we are adding, we are multiplying and adding. So, for these, just in short, we're breaking up curves. Each of these sections has a uniform width of delta x. And now, here's a couple things. One, it doesn't matter if we get the height from the right endpoint, the left endpoint, or the middle. It doesn't matter which one, because we're just estimating. We're just getting an estimation. For the sake of argument, you also don't need to have equal widths down here. What we're doing, we're always going to have equal widths, but you don't have to. All we're doing is we're using rectangles to approximate the area under this curve. There's nothing written in stone saying that delta x has to be the same, and you just wouldn't call it delta x if it wasn't constant across. But we're taking our width and we're getting our height. We're either taking our height with our left endpoints or our right endpoints or our midpoints. x1, x2, and right in between x1 and x2 is that midpoint. Just approximating for now. This is just section 1. The rest of this section, or I'm sorry, the rest of this chapter and all of Calc 2, we're going to get away from approximating area under curves. For now, this is a geometric interpretation of what's going on, or at least of what is going to be going on in our future lectures. To practice, go off and do 3, 5, 7, 13, and 21. This is fair game on the test, on the final, I should say. I'm planning on lecturing up to section 5.3 for possible final material, but it's looking like we'll go all the way to 5.5 by the end of the semester. If you guys have any questions with this, shoot me an email, let me know. Sigma notation, that you might need a refresher on sigma notation or sum notation. But really it boils down to getting your values of x from this midpoint and doing a height times a width plus a height times a width plus a height times a width. Send me an email if you guys have any questions, and I'll talk to you next time. Bye-bye.